Right, so now we're into permutations and combinations. So think about this, where we have situations involving choice, and sometimes the order is important and sometimes it's not. So if you have a 12-member club and you're choosing a president, vice president, and treasurer, so those are different roles. So if you pick the first 3 students as president, vice president, and treasurer, that's different than picking the second, then the third, then the first. But if it's just a governing council where no one has specific roles, then these 2 combinations are the same. So if the order doesn't matter, we have less possibilities. My example is the letters ACT. So in this case, ACT, acting, is not the same as being a cat. Whereas in this case, because the order doesn't matter, these 2 are equal. So the way that we calculate this, here's our factorials coming back again. So a permutations is where order matters. So order is important. So permutation, order is important. And the formula for permutation, we say n pick r, and it's n factorial divided by n minus r quantity factorial. So if we think about this, what that ends up being is we're going to start with n minus 1, n minus 2, ... We would keep going. We would get n minus r plus 1. And then the next term would be our n minus r factorial. But because we're dividing by n minus r factorial, that bit cancels out. A combination is where order does not matter. So combinations, order is not important. In this case, we say n choose r, and the formula is n factorial over r factorial times n minus r factorial. So notice it's almost the same, except that this one, we've multiplied the denominator. So down here, we've got r factorial times n minus r factorial. That's going to be greater than n minus r factorial. So since the denominator is greater, when I divide this number, I'm going to get a smaller result. So again, permutations have more results than combinations. And that's the other way of knowing. Permutations, order matters, so these things are different. Combinations, order doesn't matter, they're the same. And these are our formulas. So let's think about our formulas for our 12 students, and we're picking president, vice president, and treasurer. So if we're picking president, vice president, and treasurer, then we have 12 choices for the president gets picked, we have 11 for vice president, someone gets picked, and we have 10 left for treasurer. Well, this is saying that we had 12 pick 3. So that's the same as 12 factorial over 12 minus 3 factorial, 12 factorial over 9 factorial, 12 times 11 times 10 times 9 factorial over 9 factorial, cancels, and we got the same thing as we got with our logic. When we have a count. Okay, so now to think about part B, we need to think about the way that 3 people can be arranged. So if I've got 3 people, A, B, C, the way that these can be arranged is I've got 3 choices for the first place, 2 choices for the second, 1 place for the third. So I've got 6 possible combinations. And if you think about that, that's going to be ABC, ACB, BAC, BCA, CAB, CBA. So we've got 6 different ways that 3 people can be arranged. Well, the 3 people that I have are my 12 times 11 times 10, So these are the total number of 3 people combinations I would have, but now I have to divide by this 6 because the order doesn't matter. So if I don't divide by 6, then I've got all of these, each of my combinations in sets of 6 happening. So ABC is the same as ACB for my 3-person council. So let's compare that to the formula for N choose R. So we have 12 choose 3. Choose 3, and we're going to get 12 factorial, divide by 3 factorial, times 12 minus 3 is 9 factorial. So I've got the same thing, 12 times 11 times 10 times 9 factorial, divide by 3 factorial, 9 factorial, the 9's cancel, whoops. And I end up with 12 times 11 times 10 divided by 6 like I thought I would. And so that is the difference between permutations and combinations, and we're going to come back and look at some more examples of that.